What if the biggest constraint on hypersonic propulsion and next-gen turbines isn't the design, but whether the material can survive 2200 to 5000 degrees Fahrenheit in the real world? Welcome to Industry Ignited, the podcast where we explore the leaders driving transformation across industry, manufacturing, and breakthrough technology. I'm your host, Dr. Leanne Aguilar. And today I'm joined by Dr. Ed Pope, CEO and founder of Mach and Supercarbon Composites Technology, a world-renowned technologist and subject matter expert in high-temperature and ultra-high temperature ceramics, ceramic fibers, and ceramic matrix composites for extreme environments. Dr. Pope, welcome to Industry Ignited.
Thank you so much, Leanne. It's a privilege to be here and to participate in your outstanding podcast series.
Well, thank you. I'm excited to learn all about material science today. Now, you earned your BS, MS, and PhD in material science and engineering, and then founded MadTech in 1989. What pulled you from academia and research into building a commercial materials lab, and what problem were you determined to solve from day one?
Well, I decided to create MadTech for a couple of reasons. One is I didn't feel that in the structured corporate environment like the large research labs that they had at that time, I'd have the freedom to be able to innovate new technologies and also time it. For those who are old enough to remember, 1989 was about the time that the Berlin Wall came down. And we saw a lot of cuts in defense spending. So many of the companies who were actually eager to hire me back then, it turns out they probably would have been laying me off in about 6 months to a year anyway. And I knew that. I didn't pursue academia also because to so much of an extent, the golden age of the research university in the United States, which existed from the late 50s all the way through the late 1980s, was passing. Vannevar Bush, he was an uncle of the late George Herbert Walker Bush, who was a member of Congress, pushed the modern research university in defense spending. And that's why the United States was able to leap ahead of everyone else on the planet in terms of the innovations at the universities. But by 1989, that era was fading, and it has faded since then. Anyway, I thought MadTech would be a way to innovate, and I think it was the right choice. I'm very pleased with that decision, and it's allowed me to work on a number of startup companies, spin-off companies, if you will, and work on so many exciting challenges across material science and engineering, optics and electronic materials, high-temperature materials, fibers, composites, aviation materials, propulsion materials, heat shield materials, all sorts of things. So it's been a lot of fun. Then just in the last few months, I launched Supercarbon Composites Technologies, which is focused exclusively on carbon-carbon composites.
Yeah. Now, like you mentioned, you've worked across a lot of different types of materials across glass, ceramics, fibers, and composites. Was there a defining inflection point where you realized extreme environments materials would become mission critical across defense, aerospace, and energy?
Yeah, that was about the mid to late 1990s. Looking at what DoD was working on, had in its arsenal at the time, new materials were going to be needed. And also, DoD, now DOW, recognized that too. And through the course of the 1990s and 2000s and early 20s, the U.S. has spent many tens of billions of dollars on new high-temperature, high-performance materials for defense applications. Tremendous amount of materials, including materials at MadTech.
Yeah. And you've served as an adjunct professor and also built industry programs. How did teaching and mentoring shape how you communicate complex material concepts to decision makers who aren't material scientists?
Well, Einstein said it best. Keep things as simple as they can be, but not simpler than they ought to be. And another role model or someone I looked up to and I had the privilege of meeting and knowing many, many years ago was Dr. Richard Feynman. And he was absolutely extraordinary in his gift to take some of the most complicated ideas, concepts, theories, and communicate them in a way that intelligent lay people could understand. And it's something vitally important in teaching and inspiring young people, inspiring the next generation of young minds to go into material science. Because material science is actually extraordinarily complicated and it crosses many disciplines.
Right. Yeah. And with 30 plus years in the field, what's one assumption about advanced materials that you believe early in your career and later had to revise as the industry evolved?
Well, I'd say there's two things that perhaps when I was young I was naive about, and I'm certainly disappointed about now at this stage. And one is the unwillingness of the major prime defense contractors and to adopt new innovations. There is a desire to hang on to the legacy materials. I was frustrated that, back in the 90s, NASA, Department of Defense, and other agencies were using so many materials that were developed in the 1950s, 60s, and early 70s. And why weren't they using newer stuff? As I said, DoD recognized this, and they funded tremendous innovations. And here we are in 2026. And for the most part, the prime contractors just don't want to adopt stuff that's new. It costs too much to qualify it. It takes too long. It's a lot of bother. The program executive offices at DOW, I'm still getting used to the new title, right?
Right.
At DOW, Department of War, they keep going back to legacy materials as well. And it's like, why did you spend all this money developing incredible materials? And then your instinct is to not use them.
Right.
And that's a frustration as well. So those are two things that I don't know what I would have done differently. Become a lawyer? I don't know in recognizing that, but it's certainly been a source of frustration. And not just for me, for everybody who's in the business of innovation. Is surprisingly the lack of innovation when it comes to materials overall.
Yeah. And do you think that's primarily because of budget constraints, or is it because of the risk factor and in fear of trying new, or time? Is it because of the length of time it would take to test out the new materials? What's driving that?
Well, it's a combination of everything you just listed. You said it beautifully. You've got in any group of people, a corporate structure, a panel of blue ribbon experts, you have a risk aversion. It's just the way humans are built. You put a bunch of people around a conference table, and who's the guy that's going to raise his hand and say, well, I want to go, I propose we take this really risky new thing over here that'll make our missile or capsule perform so much better. People tend not to want to raise their hand and do that. And I think that's part of it. But the other is when we do finally address a concern, hypersonics is a perfect example. We were ahead. The United States was way ahead of everybody. The Soviets, later Russia, China, anybody else, the Europeans, Iran, you name it. We were ahead of everybody. And then Obama came into office. And for whatever reason, pretty much all hypersonic work in the US came to a grinding halt. And I know that personally because I had a phase 2 SBIR program with NASA on hypersonic materials, working with Boeing. And we were set to receive this phase 2 award and contract. And the hypersonics budget just got wiped out. And in DOD at the time, DOW now, the same thing happened. And so 10 years later, President Trump came in the first time, Trump 1.0, and he said, oh, wow, we are really behind everybody in this. We've got to catch up fast. And that was right. He was absolutely right about that. And he said, we've got to catch up fast. So an order was given out of the Office of the Secretary of Defense, no new materials. We only want to fly Legacy because Legacy has been proven. And if it doesn't perform as well as we need, we'll just engineer around it. We'll take a systems engineering approach because we got to get these things airborne fast. And that haste put all the advances, it basically took 35 years of advanced materials and pushed it off the cliff in terms of being considered for those programs. I understand why that was done, but I think in the long run, it's very short-sighted. But that's what
Right.
under
Yeah.
Biden, interestingly enough, a lot of things changed under Biden from Trump 1.0, but a lot of things just went on autopilot, and our developmental work in hypersonics just kept moving along, and pretty much under the same guidelines. They started looking at a few things, dipping their toe in the water on a few advanced materials that had been around a long, long time. I think only now they're beginning to realize that if you want to go Mach 12 in a hypersonic cruise missile, you're going to need some new stuff.
Yes, exactly. So, like you mentioned, I mean, it's short-sighted in the way that, I mean, for the time being, there's a certain administration, they're saving the costs and they're doing what's safe and moving forward. But in the long run, we may fall behind because we don't have new R&D letting us know what's going to work for new innovation in the future.
Yeah, I mean, I think that's a risk. It's certainly a risk. Before you need Mach 12 hypersonic aeroshells and nose tips for a hypersonic cruise missile, that's a particular class of hypersonic weapons. There's two other classes that already go at extremely high velocity that innovative new materials like supercarbon composites technologies is offering can make a big difference. Hypersonic cruise missiles, the biggest limitation there is right now is propulsion. Being able to propel these missiles at greater than Mach 5. And you saw there was work just demonstrated recently with Lockheed and GE on a new propulsion system that's getting up to about Mach 5 and 6. Rotating detonation scramjet, I believe, is the technology. So they're making progress, and they're going to make a lot more progress. A rotating detonation rocket engine will be able to get to much higher speeds, and that definitely is going to need a new class of materials than what they're using today.
Yeah.
So it's coming. It's inevitable that if we want to have weapon systems that far outpace our adversaries, we're going to have to move in this direction. So.
Mm-hmm. Now, you specialize in the 2200 to 5000 degree Fahrenheit regime where normal materials engineering breaks down. When you evaluate a candidate material for an extreme environment, what are the non-negotiables like oxidation resistance, ablation behavior, creep, thermal shock, emissivity, microstructural stability? Where does your mind go first?
Well, the first and foremost is ablation resistance. In other words, when you're heating something to 5,000 F, how fast does it ablate in the mission environment, whatever that is? But the second is reusability. How one of the keys to ablation resistance in some materials, like in Matech's carbon zirconium oxycarbide, carbon Xeroc, as we call it. This is a straight nose tip. It's designed to go to 5,000 F for a missile. One of the reasons that material has an extremely low ablation rate, it's really reusable material. It would be classified as a non-ablative, as opposed to the heat shield on Orion, which is highly ablative. Two different ways of dealing with lots of heat. Both very good, but depends on what you're trying to do. For a system where you want shape to be maintained, like a nose tip, and you want to fly with as low a weight penalty as possible, then you want a non-ablative material. Truth is, everything ablates. There is no such thing as zero. We mathematically, we say there's infinity as well, but everything asymptotically approaches infinity and everything asymptotically approaches zero. But in any event, to have a non-ablative heat shield, one of the things you need built in is some form of protection. And that's key. And that's one of the innovations of Mattek's carbon Xerox heat shield technology is it forms a very thin, highly adherent, and very protective zirconia layer on the outer surface that helps reduce any further recession. As far as high temperature creep, that's very important. But when you're looking at a heat shield material and you say, okay, I need it to withstand 5,000 F. Well, here's a piece of material. As you see, it has a thickness. This is about a half an inch. This is carbon-carbon. Anyway, this surface gets super hot. This surface is pretty cold. Most of your material that bears the load as a structural heat shield is much cooler than 5,000 F. So that's not as big a deal as people think it is. But where the action is on the surface. That's where things ablate. That's where things don't ablate. It depends on the material and its properties.
Okay. So you've created a heat shield, though, by putting additional material on the outside that helps prevent that.
Actually, I don't put additional material on the outside. It's engineered to form this protective zirconia coating in use, in situ.
Oh, okay. So tell me about that.
Yeah. Well, zirconium oxycarbide is the matrix phase. In extreme environments where there's some oxygen around, of course, it's going to form an oxide zirconia, in this case, a stabilized zirconia, that becomes a very thin, very protective, adherent film. If you get some form of damage to the surface, like a scrape, well, it's going to form new protective zirconia on the surface. Much like it's basically engineered to be like stainless steel. We all deal with stainless steel. Most people don't realize that stainless steel, because of the chromium that's in the alloy, forms a chromia layer that's thin, it's transparent, you can't even see it. But that's why it's stainless, is because of the chromia. Now, what's great about it is if you should wipe that off or scrape it off, the material that's exposed underneath immediately heals and forms new chromia to
Oh,
protect,
wow.
which is why stainless stays stainless.
So interesting. Okay. So for ceramic, matrix composites, and UHT systems, what tends to be the real limiting factor in the field? The fiber, the matrix chemistry, the interface, joining coatings, or manufacturing variability? And how do you prioritize trade-offs?
Yep. I think the biggest limitation for certain applications is temperature. The challenge for those of us who develop and make materials for customers is the insane regulatory environment required to qualify anything to fly on anything. We have become a horribly bloated, bureaucratic state in this country. It's just, you understand that for human passenger travel, like an aircraft that you and I would get on to go to a conference or go see our relatives, obviously you want to make sure everything's safe. You want to make sure all the parts that are critical on that vehicle aren't going to catastrophically break, endanger our lives, and so forth. Got it. We all know that. For military hardware, the Pentagon has become, in the last 30, 40 years, insanely risk adverse. This has bloated the cost of all of these defense programs. They take decades instead of years. They cost hundreds of billions instead of a few billion. And it takes forever to get innovation fielded. We talk about the incredible technologies that are in the field today that we're seeing, like the B-2 bomber and how it effectively neutralized the Iranian nuclear sites, last summer. And we talk about, when they captured Maduro, there was a sonic weapon that was used to paralyze the soldiers, the Venezuelan soldiers whose job it was to protect Maduro. Well, they were on the ground grabbing their ears because of this sonic weapon. Well, that's new. At least it's new for us, to know about. And it's great. The B-2 bomber is ahead of anything anybody else has, and that's wonderful. But that's old technology. That was commissioned in the 80s by Ronald Reagan.
Right.
Most people listening to your podcast weren't even born during Ronald Reagan's presidency. I'm obviously a little older. Ronald Reagan was the first president I got to vote for in 1980. Anyway, the thing is, this is cutting edge compared to what a lot of countries have, but it's still way behind what we could have. And, if you've ever been to Dayton, Ohio, which you probably wouldn't go there unless you were going to visit the Air Force Research Lab at Wright-Patterson Air Force Base, which I've done many, many times. They have an Air Force museum. It's very fascinating for people who are aviation buffs and geeks, people like me, to go through it and see they have every plane that was ever commissioned by the Air Force from
Wow.
the very first planes up to the present day. But one of the things that struck me, you look at the pace of change in aviation in the teens, the 20s, the 30s, the 40s, the 50s, and 60s. It's remarkable. They would go from a blank sheet of paper and an idea to having a prototype at a base flying in 2 years. We can't do that in 20 now.
Wow.
Something's wrong here.
Right. And is that because of budget primarily?
Well, no, it may be used as a rationale for it, but it's not. In fact, what's going on is actually bloating the budget. Why should an F-22 Raptor cost $160 million each? $500 million for a fighter plane. I mean, yes, it's a wonderful plane. Lockheed Martin did a phenomenal job, yes, but it's $500 million for a plane. That's ridiculous. But it's all because of the sunk costs that have gone into developing it. When it takes you 20 years to develop and field an aircraft, your per unit cost is going to be prohibitive.
Right.
That's part of the problem. And the whole, Eisenhower warned about the military-industrial complex in one of his parting speeches as president. And he was right. It was already starting. And I think things are changing. We're seeing a lot more technology being pioneered by newer companies, younger companies in the private sector. And I think it is starting to force a change in the bureaucracy. And I know Secretary of War Hegseth has been pushing to overhaul the defense procurement process from the ground up because things are taking too long, they're costing too much, and it's compromising our readiness when we need these platforms.
Yeah. So what's the solution? How do we get out of that rut and speed up the process?
Well, that has to be done at the White House, Pentagon level and matriculate down through the contract specialists. I mean, when I got a contract from DOD, you deal with a contract specialist, and it's insane the amount of paperwork is required for even a small contract. And it's a very old-fashioned process to do these contracts, to execute them. And we have a lot of what are called DFARs, Defense Finance Accounting Regulations, and FARs. And at the end of a contract, you will see pages. They're just lists with DFAR numbers and then FAR numbers. And all of these regulations are included by reference in the contract. And you are required, as you sign your name, you're required to abide by all of this stuff. The amount of paperwork and overhead involved in doing a defense contract compared with working with a private sector company on a program. I have quite a few private sector clients, customers right now. It's night and day. If you are a defense contractor, you have to have people just to handle this. When MatTech was 12 people, I had one person who did nothing but contracts and regulatory affairs. One whole job just to handle that. And it bloated our overhead rate tremendously. So
Right.
we need to cut a lot of that.
Now, you've been deeply involved in UHT fibers and composites for demanding applications like hypersonic TPS and propulsion. How do you translate lab success into flight credible reliability, especially when the failure modes are coupled?
It's really difficult. You can succeed at doing something at a lab bench, and then when you try to translate it into the macro scale and into production, it's a whole different ballgame. And we see this in medical research all the time. We're constantly seeing a professor at a university somewhere did an experiment with a mouse and he cured diabetes. Yay. And then 20 years later, you're still waiting for that. Well, there were some fundamental problems with whatever it was that prevented it from ever getting scaled up.
Right.
And you see that in advanced materials a lot. When you develop something that is very hard to make on a small scale, and then you try to make it in bulk, and the properties degrade, or there's a fundamental supply chain issue, or one of the ingredients is prohibitively expensive, and on and on. Fortunately, I've had 35 years of experience in dealing with that sort of stuff. And so when I come up with a solution to a problem, what I've tried to do is look at it from the point of view of, well, I'm going to need to make this in bulk. And if it's not me, it's going to be someone else who's licensed or working with me. So I need to start with an approach that is inherently scalable. Today, as important as it's been in the past, but today, more important, the supply chain.
Mm-hmm.
If there's a key ingredient in well, let's take carbon Xerox as a ultra high temperature composite. There are certain key ingredients without which you can't make the Xerox matrix. Well, turns out those key ingredients are all made in the United States in bulk today. All the key ingredients I need for that zirconium oxycarbide matrix, I can acquire in literally freight car loads. If your facility has a railroad track coming up to a dock, a receiving bay, then you can buy huge freight car loads of the material and bring it to your loading dock. So it's got scale. It's 100% domestic to start with. So scaling this up, from that point of view at least, is built into the technology.
Right.
Same thing when I developed much more recently the fast densified carbon-carbon. It's relying on a supply chain that is already scaled up, domestic, and technology that's already scalable to make the material.
Yeah. So considering these from the very beginning, from the R&D stage, is important, is what I'm hearing.
I think it is.
Yeah.
I think it's very important.
Right. And do you think about that a lot from the start, or is that something that people tend to put off and then realize it's going to be cost prohibitive, or they're not going to have access to the materials to scale?
Well, I think industry people think about it a lot more than, say, university researchers. And you would expect that,
Right.
because industry makes things in bulk, usually. In a university research, what's the primary goal of a successful professor? It's training young people to tackle the problems of the future, and it's also making discoveries. If they're in a research university that does a lot of research, they're making discoveries that may not translate into a practical product for 10, 20 years. And that's okay. We have a need for that kind of forward-thinking innovation. There's nothing wrong with that. I think sometimes they want to move it from the university lab bench into production. They think it's valuable, and they wonder why, for the most part, is industry just not interested now? Is because it's not mature enough.
Right.
The way we look at a technology is we rate it as on a TRL, technology readiness level scale, 1 to 10, and an MRL, manufacturing readiness level, on a scale of 1 to 10. And in industry, we look at that very closely, very carefully. And a lot of the stuff, when it's an initial development, has a very low TRL and MRL.
Yeah. Yeah, and that makes sense. So at the university levels, it's conceptual. Like you said, the focus is on creating new innovations and discoveries. But then when you take it into industry, it's a different set of considerations that they have. They're looking to how practical it is, how affordable, how scalable, and how can they move it into the manufacturing process.
The term we use to describe that gap between where, say, a professor or an inventor thinks they should leave off and industry should pick up, and where industry thinks it needs to be brought to before it's willing to pick it up, that gap is called the Valley of Death.
Yes, the infamous Valley of Death, right? Now, Dr. Pope, you've developed multiple technology families. Which material platform do you think the market still underestimates and why?
The biggest thing is not listening to the customer. If you're trying to promote your own solution to a problem that the customer doesn't think it has or isn't aware that it has, it's the difference between technology push and market pull. That's the key. I'm pursuing what I think is the biggest market opportunity. The technologies I've developed that I'm not pushing right now, there's a reason. It's a technology push, not a market pull. And I've looked at it and I'm not sure where the market pull would come from. If you're an inventor of materials or anything, I mean, look, Thomas Edison had over 1,000 patents to his name.
Right.
Yet the handful of things he's renowned for are probably less than 20 patents, maybe.
Uh-huh.
So what happened to the other 980? They didn't go anywhere.
Right.
It's better to ask the market what it needs and try to fulfill it. A perfect example, timely, is the fast densified carbon-carbon composites. The biggest thing that, for me, as a material scientist, I'm promoting are the benefits of the technology. Carbon-carbon's around. It's a $20 billion a year industry today. It could be larger. I'm promoting that fast densified carbon-carbon will have a higher wear resistance for aircraft brakes, higher ablation resistance for nose tips and missile propulsion. And that's great because that's all true. But when you ask people, and for the last 3-4 months, I've been talking to people, privately, of course, and you ask them, what do they want? They want cheaper and faster. Oh, yeah, we'd love better. Better is wonderful. You've got a better carbon-carbon? Yeah. But is it cheaper and faster? Because that's what we're struggling with. The time it takes to make the parts and the cost it takes to make the parts. So one of the things, I'm announcing it on your podcast for the first time for Super Carbon Composites Technologies, we do have a way to make carbon-carbon cheaper, faster, and better all at the same time.
All right. So tell me about your technology and the opportunity it brings and the benefits.
Well, the benefits of supercarbon composites are, as I mentioned, much greater wear resistance for things like aircraft brakes, which translates to time on wing, which is something airlines really care about. Aircraft that are sitting in the maintenance hangar are not generating revenue for the airlines. So the more time they have to be out of service for maintenance, inspection, repair, replacements, the more time they're not making money. And the airlines, as you know, is a very competitive industry. The margins are pretty low. So it's a huge benefit to the airlines, who are the consumers of landing gear assemblies that have carbon-carbon. Now, what do the manufacturers of carbon-carbon brake material want? Well, they want an advantage, a technology that makes it cheaper and faster to produce the same brakes they're making now. oh, we can make them last longer. Well, that's also a competitive advantage. But we don't want to pay extra for that. Most of the time, industry does not want to pay extra for improved performance. It's one of those things you say, well, how can that be? And it's like, for the most part, it's true. There are exceptions, but mostly they don't want to pay extra for the performance. But they sure will pay extra if they can make the product cheaper and faster.
Right.
That's what they want.
Yeah. Now you've taken 25 products from R&D to market, which is rare in deep tech. What does your commercialization playbook look like? Qualification pathway, early adopter selection, manufacturer scale, strategy, and risk retirement.
All of the above, of course. But I think identifying what the real market for the technology is right at the beginning is first and foremost. There's no point inventing a solution to a problem that doesn't exist or isn't perceived to exist. You need to solve the problems that the industry is asking for. A perfect example is a product line that I developed at MatTech, fluorescent reference standards. I was approached in the mid-90s by a large company that does assays. When you go get blood tests, particularly the type of blood tests that use polymerase chain reaction, PCR, a viral load, detecting HIV, cytomegalovirus, hepatitis B, even if you want to do detailed tests for COVID, and many other things. You use PCR, and it's a fluorescence-based assay, and which is wonderful. These machines that this company had, you load a tray, a microtiter plate with 96 wells in it, and with all your little tests, 96 individual tests. You load it in the machine. It goes through all this cycling, and then a day or so later, you get the results because it has to grow the antigen that it's looking for. Now, what the problem was is because it's a medical test, they need some way of referencing it. They need a standard because these machines read these 96 little wells on this plastic tray. Well, how do we know the reading numerically is the same across it? Well, it turns out the instrument was 40% off from one end of the plate to the other.
Wow.
Yeah, that's pretty big. They didn't know.
Yeah.
I had to make a fluorescence reference standard, a material that would last for at least 3 to 5 years. Turns out it's indefinitely. That was uniform, so that there is a coefficient of variation of the absolute intensity of the fluorescence of this tray of 1% across the plate. And I developed it and launched it as a product. It became manufactured under GMP, Good Manufacturing Practices, which is part of FDA, licensed by the state of California Food and Drug Branch, and also Class 1 510K exempt medical device by the FDA, blah, blah, blah. A lot of quality control management system had to be implemented to do that. Anyway, this became a tremendous product line and sold over 10,000 or more units of these things. And they were priced at the time between $600 and $800, even as high as $1,200 a unit. And that sounds like, okay, that's a lot of money.
Right.
But they lasted indefinitely.
Okay.
And I sold that entire product line to a company in the UK, which makes them today. And that was about 20 of the products.
Yeah. Wow. Did you still have the license for that particular innovation?
I sold the technology.
Okay, so the whole technology. Got it. And did you develop it for them, or was it something you had you just found the buyer?
No, I just actually the buyer found me.
Okay.
I had developed the technology in the 90s, put it into commercialization by the late 90s, and doing a lot of sales on it. And I had a whole separate little unit of MatTech dedicated only to that product line. And that's great. But the
Okay.
rest of MatTech was working in high temperature aerospace defense materials and growing in those areas. And this technology was very different from everything else we worked on. And so this British company that makes their specialty is nothing but standards, optical standards and other kind of standards. This was perfect fit for this was right in the wheelhouse of what that company did as its primary mission. And it was
Got it.
off to the side for Meta.
Okay. So it just fit better with what they were up to, and so they purchased that part of
Yeah,
your
exactly. And it
business.
was a
Got it.
fully mature technology in production for years and years.
Huh?
One of the things we ended up having to do is recertification. A company would send a tray back, and for a few $100s, we would recalibrate it, certify it, and send it back. And we made a lot of money on that. The materials were designed to be basically stable forever. I had standards that I'd sold, well, now it would be 30 years ago, that were being recalibrated for the sixth time. And the standard had actually passed through the hands of a dozen different people at that company over time, had inherited the standard anyway.
Now, you negotiated multi-million-dollar licensing agreements and built a significant IP portfolio. How do you decide when to manufacture in-house versus license? And what signals tell you which path creates the most value and the fastest adoption?
My rule of thumb has been tech would only manufacture in-house things that were low volume and high value added. Any technology that needed very high volume was a candidate for licensing and tech transfer to a really large company. And the reason for that is pretty obvious. As a small company, you don't have the facilities, infrastructure for high volume production. Also,
Right.
a state like California, where MatTech's always been based, we are not the ideal place to do high volume manufacturing. Our labor rates are much higher, real estate is higher, regulatory compliance is higher. Everything that's a cost to doing business in California is higher than other states. The only way you can make money in California is stuff that's very high value. I mean, you see the tremendous innovation in California. It's all things that are high value added.
Mm-hmm.
The latest AI software algorithm. Entertainment industry has always been pretty high value added, and you look at the cost of movies to make them. But even that the thing is, even as companies get more mature, you notice a lot of high tech companies have moved to Texas and Florida and other places because it's gotten prohibitive here. So
Right.
that's always been a practical consideration. The other is that I had no desire to have a factory with 400 workers and 100,000 square feet. That's just not. That's
Got
not.
it. Right. Okay, so it was an intentional choice. You focused on creating more innovation instead of
Exactly.
scaling what you had. And so once it reached a point where it needed to be scaled, you would just sell the technology instead of taking.
Yeah, exactly.
Yeah. Great. So for companies trying to buy or license advanced materials technology, what do they often misunderstand about readiness, the gap between a promising material and a production grade supply chain?
Well, it depends. Most serious companies that have experience do understand pretty much everything you just listed. Some companies, not as much. And I think sometimes they underestimate what it's going to take to move from the lab bench into the production environment. Or put another way, they think it can be done a lot cheaper than it really can be done. And so when they find out the
Yeah.
cost of things, they're surprised. I said, well, you shouldn't be, but okay.
Right, exactly. So is that's part of the process then consulting, getting them just really familiar with what they're actually looking at cost
It,
wise.
sometimes it takes a bit of hand holding and educating, which is part of business development. I mean, that's part of the job. Yeah, this is probably going to take just a little more than you think it will, but here's the payoff. Here's what you're going to get that your competitors won't get. And that's very important.
Now, a lot of organizations talk about innovation, but procurement and qualification can slow everything down. How do you help large organizations move through gate reviews and compliance without diluting the technical intent of the material solution?
It's very hard to do. When you're talking about large defense contractors, the Lockheeds, the Raytheons, the Boeings, Northrop Grummons, the others, particularly the big four contractors, they have a bureaucracy that is so entrenched. Don't think you're going to change it. You just got to live with it, work around it, because it's just part of the culture, and it's just entrenched. And there was a time 50 plus years ago, we didn't have 3 or 4 massive defense contractors. We had 50.
Really?
There was a hell of a lot more competition. When
Yeah.
DoD wanted an aircraft, there were many companies lining up with their proposals of what to do. So everybody had to compete, and it was an aggressive competition back in the day. But over the decades, there's been a lot more, tremendous consolidation. And so there's less competition. And I think, and it's not to say that anybody's bad or evil, I think it's just the nature of the beast. When you get down to only 3 or 4 competitors at best, that's not competition anymore, because that's too few players to keep track of. I'm not saying anybody colludes. There's no nefarious cigar smoke meeting behind closed doors with a bunch of old guys conspiring to, this sort of, no. But everybody knows what's going on with everybody else. They all look at each other's knickers.
Yeah.
Can't be helped, particularly since it takes so long to get anything done. You got plenty of time to know what your competitor's doing.
Mm-hmm.
You can't pull like a Howard Hughes back in the 30s and 40s and suddenly unveil a brand new aircraft that nobody saw coming. It doesn't happen anymore. And so as a result, not saying that there's anything nefarious going on, it's just the way it is. There's a complacency.
Right. I was going to say that true spirit of competition is gone then.
Yeah, when you have only a couple of players that are competing.
That makes sense.
You really have competition, you might as well only have one at that point.
Yeah.
I'm not advocating that at all. I think we should go in the other direction.
Sure. It just what happens, right?
Yeah.
Now, you've said that modern constraints in aerospace and advanced systems or materials problems. Where do you see the next major breakthroughs coming from? New chemistries, better architectures, better processing scale, or smarter qualification models?
Of the 5 things you listed, I'd say the last 2. I don't think we need new materials. Maybe new to some people because they didn't hear about it before, but in terms of being truly new, I don't think we need new materials. We have so many materials already that could be immensely impactful. I even have a few, and we just haven't exploited them yet. We haven't leveraged them anywhere near how we should or could to get more performance out of these systems. You can get away with a system engineering approach to demonstrate an engine, a propulsion system of some sort. And maybe the materials are nowhere near optimized, but you're only going to fly it for a minute as part of a test program. You don't need to spend the money on the material. Demonstrate, because you're not demonstrating materials, you're demonstrating a design. You're demonstrating a system engineering approach that you want to show works. It's a new propulsion system, a new design for a propulsion system. But if you want it to fly reliably and manufacture in bulk, then you're going to need to apply the new materials. I think that's where a huge opportunity is right now. People are starting to wake up to the fact that they need things that are better.
Yeah, right. So finally, for engineers, founders, and R&D leaders who want to build enduring careers in advanced materials, what's your best advice on developing technical depth and the business fluency needed to get real-world adoption?
That's another big question. I think in the universities, one thing, you're learning theory, and that's great. And you're learning your phase diagrams. As a materials engineer, I had to memorize the iron-carbon phase diagram and a lot of others. And that's great. one thing you need more of as a student is hands-on. I think for the university is, of course, a great opportunity to learn principles and theory of material science, but you need hands-on. One of the greatest opportunities I had starting as a freshman is I was hired into a research lab, and I started out literally washing test tubes and beakers when I first joined Professor Mackenzie's lab at UCLA, and quickly became an assistant for a grad student. And I spent so much time in the lab, as much time in the lab as I spent in classes. And I started getting my own projects. And I was the youngest student to have his own project with my professor. I was a junior and I had a NASA project. And usually that was reserved for doctoral students. And I remember the day he came to me and gave me the project. He says, Ed, I have a program that started 6 months ago. It requires a grad student, a postdoc, and an undergraduate. I have nobody. I'm giving this project to you. You've
Wow.
got 6 months to do something with it. Anyway, I did. And it ended up being the first paper I ever gave at a professional meeting while I was still an undergraduate. And I took it to it like a duck to water. And of course, by the time I was a grad student, I was a royal pain in the ass to the professors because they would be talking about certain things that I knew a lot about, hands-on. And, they'd say something. And I said, actually, if you do it this way,
Yeah.
this is what you'll get.
Right.
And, anyway, so hands-on. But I don't think that being an entrepreneur is right for everybody.
Yeah.
There's a reason only 2% of the population are leaders. Is because it takes, not saying that I'm a leader, but I've survived. It takes a certain type of personality, and not everybody has that.
Yeah, and it's a lot more than just doing the thing, and it's more than the engineering or the technology or the material science, right? It's running a business, it's doing all of the other things and managing people. So, right, it's a different set of skills. And I do agree though, the hands-on experience, I mean, there's no substitute for that. I mean, there's conceptual knowledge and theory, like you mentioned, but when it comes down to practice and implementation, that's a whole nother ball game, and you gain so much more insight and depth of understanding by actually getting your hands dirty, right? And getting in
Absolutely.
there.
And
Yeah.
trying things. I've been told many times I'd pass an idea in front of a grad student or postdoc when I was younger. And they said, no, that's not going to work. Here's why it's not going to work. Okay. Then I go in the lab and I do it and it works. And I said, and here's what you missed. Here's why it worked instead of not working.
Right.
I was like, oh, well, you know how to do that because you work with your hands. You observe with your own eyes what is happening, and you gain so much. AI can't do any of that.
Right.
Yeah.
No, right. Well, and it's drawing from a database of what's already been and what's already has been. I mean, it doesn't create from nothing. It creates from the existing knowledge.
Right.
So,
yeah. Exactly. And what it doesn't have, it hallucinates. So there you go.
Yeah, that too. So you've got to know the difference.
Yeah.
Well, Dr. Pope, thank you for joining me. Your work is a powerful reminder that materials aren't just inputs. They're often the boundary between what's imaginable and what's achievable. For listeners who want to learn more, where can they reach you?
Well, I can be reached on LinkedIn. I have a profile there. Just type in Dr. Ed Pope, and I think I'll pop up. Matech has a website, www.matechgsm.com. And SCCT has a website, www.supercarbon.us. And there's a page on that website where you can send me a message and I'll get back to you.
Excellent. Well, thank you again. It's been great. I really enjoyed our conversation.
Thank you so much. Likewise.
Thank you. For our listeners, if you enjoyed this episode, please subscribe to Industry Ignited and tune in for our next conversation with another leader shaping the future of industry, manufacturing, and innovation. Until next time, stay bold, stay curious, and keep igniting industry.